projects to Smart Campus. I'm Tyler. I'm a computer engineer. I have experience in telecommunication, data communication, and my role for the project will be to help enable wireless communication and test functionality of the system.
I'm John Marisi. My interests involve embedded software, embedded system design, and software development. For this project, I will be working on the hardware design as well as the software design and prototyping of the system.
My name is Brandon Zayas. I am the team leader, and I am an electrical engineering major. I have interests in power electronics, power systems, sustainable energy systems, and automation systems. Most of my expertise revolve around electronics and designing control systems. My role for this project is going to be to work on the circuitry behind the hardware for the system and possibly help with designing some of the software elements.
I'm Joseph Shahovich. I have interests in power distribution and sustainable energy sources. I have expertise in electronics and power distribution for building scenarios. For this project, will be focused on the hardware aspects, specifically the circuitry behind the different various components of the system.
I'm Zach Vacco. My interests are power distribution systems, control systems, and automation. My expertise is in electronics and power systems, and my role for this project will be aiding in the circuitry behind the hardware necessary for our system.
I'm Steve Toscano. I have interests in database systems and software application. My expertise is in coding, and my role will be to design the software app and create the database for our project.
Okay, so what are we doing and why is it important? So basically, we're worried about energy efficiency and energy usage specific to electricity, and the problem of wasted electricity is especially prevalent on college campuses, and it's very costly to renovate a building and redesign certain aspects of it to be more electrically efficient. So what we're doing is we're using the Internet of Things phenomenon to create a very modular system that can be applied on a classroom by classroom basis to basically monitor power usage and control plug-in load usage and wasted electricity specific to computers, lighting, and outlets.
So our project, we explained how we're focusing on the power usage aspect of a smart campus, but it is also important to explain that this system could be expanded beyond just a power usage controlling system. So we could include campus security, life safety, fire alarm, smoking systems, and it could be, we're going to work on setting up the system on a per room basis, but of course the system in a whole could be expanded throughout the entire building. It could also, it was mentioned to us, include parking for the school campus parking.
Just to add on to that, it's important to note that our project is basically a building block into the whole big picture of a smart campus system. As Joe said, it can incorporate all these different features. We're just focusing on the power management aspect of this. This isn't a project that is aimed to be completed in 1 year. This is something that we're starting that hopefully can be improved upon in years to come and upscaled, and different features can be added to it. Different smart features can be added, and eventually this can be used across campus and completely envelop the idea of a smart campus.
Okay, so if you look at this is a typical classroom, and there's a few things wrong here in terms of power usage. And that would be that things have been left on, including the air conditioner, which you just have to trust me that it's on. The problem is, the computers and the projector are very often, they will go into a low power state on their own. but very often they won't. And in this picture, there's nothing really directly plugged in, but a lot of times there are plug-in loads that will just be left on needlessly when someone walks out of the classroom. And a lot of classrooms also don't have automatic light sensors, which is another thing that can get left on. Next slide.
So the state of the market, a quick Google search can tell you how the smart market or the smart building market is thriving currently. Right now this year there's a $5.7 billion market, and it's projected to grow to $24.73 billion by 2021. So you can see how many people are moving towards trying to get smart building designs, and obviously there's no sign of slowing down. And reasons for this are increased urbanization, which on its own has led to social and environmental challenges. So some of these challenges are water shortages, power deficits, pollution, wastewater, and sewage problems. And creating smart buildings, although more expensive maybe up front, are a way to combat these challenges that I just spoke about. So analyzing the competition, one of the competitors that we looked at was Lutron. And Lutron is a company that's well versed in smart switch technology and controlling hubs for lighting controls. So anytime you see a company that has sensing technology for the lights or for the shades, it's something that Lutron specializes in. So now they're trying to aim their systems that they've had in place for sensors, they're trying to aim them towards energy saving controls. So they have the energy saving light controls, which saves energy by turning off the lights in any unoccupied rooms. A smart shade system will reduce the glare in a room, so it can sense where it needs to be to reduce glare, and it'll also lower solar heat gain, which saves energy in turn. Another one that is a competitor is Acuity Brands, and we look at them as more of a direct competitor than Lutron, because although Lutron has the smart sensing technology, Acuity is really more groundbreaking in this sense. They specialize in smart lighting networks, but that's not all they do. They have technology to transform energy-efficient LED lighting into a smart connected platform for data-driven applications through an alliance with sensitivity systems. So, although they are at the core a lighting company, they have a technology now called Byte Light Indoor Positioning Technology, which increases the understanding of how occupants may interact within a large-scale indoor environment. So it'll see where people tend to go more often, at what time during the day, where foot traffic might be. And this technology creates a new opportunity for data analytics that leads to operational efficiencies, enhanced safety, and increased revenues in large spaces. Because you can imagine how a large space may get pretty costly if everything is being left on when people aren't there. So Byte Light Indoor Position Technology kind of gives the client a better idea of where and when people are. And they also recently acquired a geometry platform, which is a comprehensive mapping tool that helps them identify, measure, and visualize foot traffic. So that's just another way for them to aid in giving the client the best and most up-to-date information on how their space is being utilized. So the value propositions, obviously when you're considering a smart building, there are a lot of different things that can be thrown into a smart building, different sensors, different technologies that you want to add. So there are a lot of trade-offs that you need to consider. But the one that we want to emphasize on, especially with the buildings here on campus, are energy efficiency and control design. We're aiming to create an efficient smart building with intelligent control capabilities, so the user has a lot of leeway on what they want to do. And we're placing significant importance on a high-performance system. So we're looking to create a high-performance system which is going to be scalable, because as you said, this isn't looking to be a finished product. We want other groups to come in and be able to expand upon this in the future. And this is basically just a building block that we're looking to create here for other groups to come in and either perfect the technology that we put together or add on to different types of technology, different types of sensing, whatever it is they feel is fit for our system. So our comparative advantage, obviously, like we said, a lot of companies are getting involved in smart buildings since it is projected to be upwards of $25 million industry in the next 5 years. But our competitive advantage is our energy efficiency. Since it is going to be a custom tailored system for the campus here, we can create a product that accurately notifies the user as to the amount of energy being consumed on a campus based on how we feel a campus is most efficiently used. So we'll be able to tailor the way we want to build our system for how we feel a campus can be better maintained to use less power and be more efficient. And we want to ensure that the system itself is a very low energy consumption, because obviously if we're putting the system in, it's extremely high power, and it's not, it has a high energy consumption that kind of defeats the purpose of monitoring it, because we'll just be creating our own consumption. And then another advantage that we have is our cost of production. So like I said, we're trying to create a custom tailored system to minimize the cost while maximizing control that the user has over the smart building. So we can kind of handpick what we feel is necessary for right now for the prototype for just the main campus kind of implementation. But over time, each building may have its own needs, and we'll be able to address that on a scaling basis. So right now, obviously, with such a big market, there are a lot of research projects about what can be added or innovated upon in smart buildings. And California Polytechnic State University is one of the schools that's very heavily involved in this type of research. And one group did an enterprise smart outlet, was their design project. And their goal was to allow users to change power consumption habits on a large scale, which is very similar to what we're trying to do. And they're trying to collect real-time power consumption per outlet and conform future habits to help them conserve electrical energy. So they are kind of specializing in the outlet aspect, which, as you'll find out later in the presentation, is just one aspect of what we're looking to do in a smart building. And the three main goals that they were looking at are that the outlets work in a standard electrical outlet, so you don't have to have a bunch of specialized outlets for this. They want an easy setup, and they want to easily monitor the power consumption and be able to make recommendations to the client or the user on where they can be more efficient and what can cut costs. And obviously, one of their constraints was that the device itself is going to consume a fraction of the amount of energy that they're looking to save. And another one which we feel is a little bit more similar to what we're trying to do, but obviously we have our own differences here. The wirelessly controlled smart outlet, which is a standalone communication unit that is used to connect the home or building outlets to the internet. And by doing so, they'll be able to control lighting and simple appliances through the home wirelessly, or building obviously. And in their case, they're trying to do it by controlling it through Google Calendar interface that will schedule the smart outlets with dedicated calendar events. So there's going to be a more predetermined basis where, say that they know there's a lecture from 3 to 4 in a room. It'll be on from say 2:55 to 4:05, and then there's not really going to be any user input there. Whereas we're trying to have a skeleton, as you'll find out later, like I said, we're trying to have a skeleton basis on what the classroom schedules may look like, and then we're going to include machine learning and pattern recognition to be able to get as close as we can to perfect when these outlets should be on or off and what is used at what times. So there are a couple relevant patents. This one's pretty vague. It's just a smart building manager, which was patented in 2013, and it includes a communication interface to receive information from the smart energy grid. And it includes an integrated control layer configured to receive inputs and outputs and provide outputs to multiple building subsystems. So this is basically just a software patent that they have right now, but we're obviously looking to go further than just the control aspect. We're going to be building all the hardware as well. And then the smart outlets and associated networks, which was patented in 2010. It allows standardized outlets to be remotely monitored and controlled. Multiple smart receptacles communicate with a local controller, and the local controller communicates with the remote controller via the internet. And ours is going to be slightly similar, but we're going to have a lot of playoffs of that as we'll get into as we get into the design of our system.
So in trying to figure out how to approach our system and how to approach our design, we used a pairwise decision matrix. We want it to be power efficient, which is our main goal, as you can tell, since that has the largest weight, almost half. We want it to have lots of functionality, so like lots of features, but we want to make sure that the foundation works before we start adding on, all sorts of bells and whistles. We also need to make sure that it has scalability, to make sure that it can be built on top of in future projects for future groups. We initially were thinking that we need to make it easy to use, and we need to make it very cost efficient. But we figured that only a few people are going to be actually adjusting the system, so those few people can be highly trained, so it doesn't necessarily need to be all that easy to use. And then we were not very worried about the cost, because a lot of the pieces we're going to be working with are very inexpensive.
So, what are our marketing requirements? These are the things that meet the needs for our consumers or users. So, our system has to be able to monitor energy usage so that the system knows what's being used or not. And it can also relay the information on what's being used the most. The system also needs to include automated room control. So, like mentioned, the system should be able to automatically, either based on an inputted schedule or just pattern recognition through machine learning, be able to control its plug-in loads or computers or projectors. And again, the machine learning will enable the pattern recognition for all of this, all of the usage. So here's our objective tree, which sort of breaks down our marketing requirements into more of how they can be accomplished. So for energy monitoring and control, we need load usage sensing, a manual and automated lighting control, remote device operation checking, and for automated room control, we need to include room occupancy checking, projector usage control, computer usage control, and for machine learning, we need to have pattern recognition of the room and smart data acquisition so that data can be skewed in our database based on a one-off scenario. So, in an example, if it's a warm day outside and the air conditioning is on in a building, then if someone was to open a window in a room and our temperature sensors are reading a cold temperature, the system should be smart enough to not turn that AC off in the entire building. And here is the ranking of our needs, the needs for the project. It can be seen that though each one of our needs has a pretty high importance, so they're all weighted pretty highly, but as can be seen, there's the necessity for energy monitoring is much higher than the automated room control and machine learning, but those are also important as well.
So this has already been hinted at quite a bit, but wait, is this my slide?
This is the problem statement, and this is just a summary of the previous slides. How it says how things in a campus like projectors and computers can be just left on, just whether people care or not. They just go to class, do what they have to do, and then leave, and they're not really caring about what energy they're consuming, and then things are left on. So the system should be able to take care of that and not have that unnecessary power usage when a system is something's not even being used. And our engineering requirements, these are the more specific technical requirements. Our system needs to be able to, like mentioned, either based off the inputted scheduling or the pattern recognition, be able to ready a room for class in at least 5 minutes before the class is to begin. The system should reduce energy consumption by about 25%. The system should be able to recognize similar patterns of usage after only 3 familiar occurrences, and the system should be able to be deployed in a pre-existing building. It should fit in regular standard-sized game boxes, and to install the system, it shouldn't take more than an hour for a per room basis.
Okay, now this is my turn. So we've already hinted at this quite a bit, but for our system, it's basically going to consist of smart outlets, smart switches, a sensory hub, and a application that will enable you to control these devices. The smart switch and the smart outlet will be controllable to be turned both off and on. The switch will obviously have also manual input, so you're not removing any of the standard functionality of the switch. The sensory hub will include a proximity sensor and a temperature sensor, and all the data collected from each of these components will be sent through a server to the application, which will use basically pattern recognition over time or scheduling to either turn devices on or off based on room requirements, such as say you schedule a room for a certain time, the room will turn on at a pre-scheduled time. So when you come to the room, everything's prepared, you're not wasting any time, there's no energy wasted by leaving the room on all morning while you're waiting for the class to start. It's just a more energy effective method of doing things. Obviously, one issue that would come from the system is accuracy. So for instance, with the proximity sensor, if it's incorrectly reading the proximity sensor, say there was no one inside a room, but it was detecting there was movement. All the lights turn on, things turn on in the room, you're wasting power, it's just not working correctly. And say there's people in the room and the sensor doesn't go off, then the lights turn out on you and then no one's having fun. So everything is going to revolve around the accuracy of the system in the end, so that's something we're going to have to account for through every step of the process.
So project summary, we expect our project to be fully scalable in order to equip the whole campus as a smart campus, but we're going to focus on our room. To start, the devices will all operate from grid power, and then in order to monitor their own power consumption, we want them to additionally be able to monitor the power consumption of what is plugged into them. Our system should be able to communicate with Wi-Fi. We're going to use Wi-Fi modules, so we're going to set up TCP/IP as our wireless protocol to enable communication. And then once our system is the server in which the server will then send the corresponding signals to the outlet or smart switch.
So since basically our project completely revolves around power consumption, we decided that an appropriate no-go milestone would be if we determine that our system actually isn't efficient at all and it's doing the opposite of what we want it to do. So basically, by the end of this semester, we hope to have some data to prove that the devices that we'd be installing would actually be saving energy, and we hope to do this by getting permission from maybe the chair and the dean to maybe access some information about the power usage of maybe one of the classrooms in RFC. It's also actually important to note that at the end of the 2 semesters, we hope to actually implement this into a room, not just have it as a test bed. We want this to be functioning somewhere. Unit testing. So we're going to go through 3 phases of testing: the unit testing, the integration testing, and the acceptance testing. The unit testing will involve basically testing each individual component of the system as it's being built, making sure that everything functions appropriately. Like, for instance, the outlet, switch, and sensory hub. There's different components that make up these devices, such as the relay circuits functionality. We have to make sure that that relay is tripping appropriately, passing power as needed. We want to have LED indicators on some of these devices, so we want them to actually turn on or off based on the state of the device. Obviously, we want the proximity sensors to actually detect something, and temperature sensors as well. On the software side, there will also be some preliminary testing as things are being developed. So iterative testing of functionality of the firmware and microcontrollers, the microcontroller Wi-Fi module communication, and testing of the application's ability to communicate with the server. So for the integration testing, this will be done once the devices are completed. We will integrate them to become one unit, one system basically, and as we enter this stage, we'll be able to test how everything communicates with each other. So for instance, we will have to connect all the hardware up to the room, and then once that's hooked up, then we'll have to test the communication between the devices and the server and the application, and we have to make sure that everything is being received correctly. So the acceptance testing. This is basically what these tests are going to be the final phase of testing. These are going to be kind of stress tests to make sure everything works appropriately. We're going to try to induce some errors on the system to make sure that we're not going to be giving something to the college that's not going to work at all, or just have some weird bug that no one's going to be able to figure out. So we obviously want our outlet to start in the on state, to allow power to pass the load. We don't want someone to have to really go into the program first to be able to plug something in. Obviously, the LED must function appropriately given the state of the device, and the software must be able to turn the device on and off either remotely or through scheduling or instantaneous input. The smart switch, it's similar. We also have to check the LED indication, but this device we want to start in the off state, so when put it in, it's not already turning lights on. And obviously this component should operate with a physical button press or remotely. Next. Then for the sensory hub, we want an LED on this device to show when there's power being supplied to this device. We want it to obviously send the information it's gathering out every hour. We also actually want to have some outside information for the outside weather being incorporated into the system. So while we're not initially thinking of incorporating HVAC control into the system, mostly due to the fact that for a single room you can't really have complete control, such as for this room. You change the HVAC control and it would do it for multiple rooms. So that would be something further down the line, but we want to implement that sensor into the system to begin with, to be worked on in the future. But by incorporating the outside temperature, we want to be able to determine if the inside temperature based on the outside temperature is appropriate. And then for the server, this is going to take all the information from all the devices, talking about the outside temperature readings mentioned there. And this is obviously going to have to communicate effectively with the software application. And as the software application says, there should be seamless communication between the devices. You shouldn't have to press a button and wait 5 minutes for something to do anything. It should be somewhat, not instantaneous per se, but it shouldn't take too long. It should be within the realm of acceptability. So maybe, 10 seconds if you're talking about turning on a whole room. So obviously we have to be able to control these devices both automatically and directly. We also want to be able to input new devices quite easily. We would do this by, you can explain this better than I can, MAC addresses.
Oh, yeah, so I mean,
installing new devices.
Yeah, so every time a device is added, Yeah, it would be identified by MAC address, and it would be given its own IP address, and then it could be added to the network. So I mean, yeah, you could have a room, and if you just that's the whole scalability aspect of our system. You just drop an outlet or a switch in, and you add it to the system, and there's no installation downtime really.
Yeah, so we basically want this application to be able to allow users to input new devices and schedule, configure those devices to work in tandem with other devices to function as a room. So when a room turns on, all these devices turn on together, not just individually. And then obviously this application, as I said, will be able to control devices. And an important thing is it has to, as I mentioned before, recognize states of devices. So for instance, say your outlet is registering as off when you want it to be on, you're just going to be plugging something in and nothing's going to be working, and then you're going to be confused why. Same thing goes for switches and whatnot, especially if you're controlling remotely. If you're controlling remotely, you won't actually be able to visually see if that device is appropriately working. So obviously the system has to have appropriate feedback. So here's the project timeline. We managed to squeeze this in here somehow. But it's a bit detailed, I'll say. We gave decently appropriate times based on communicating with each other as